Under a blood-red sky, the day the sun changed. What if tomorrow you woke up under a blood-red sky? Not at sunrise, not because of wildfire smoke or volcanic ash, but at noon, with the sun high overhead, and it's a small, dim, deep crimson point in the sky. You step outside. Shadows are softer, longer, as if the world is stuck in a permanent late evening. The light feels strangely muted, almost alien. And then the realization hits: the sun itself has changed. Our bright yellow G-type star has become a red dwarf. So what does that actually mean for us? Would Earth still be here, quietly circling the shrunken star? Would any of us survive such a transformation? Or, more fundamentally, if the sun had always been a red dwarf, would life have ever had a chance to begin at all? Evaluating a star system for compatibility with life is tricky. We tend to focus on the planet, on oceans and atmospheres and surface temperature, but while the details of a world matter, a huge part of its fate is written in the type of star it orbits. This means changing the sun changes everything. It should be noted that red dwarfs are not some exotic rarity. They are the workhorses of the galaxy, the most common type of star in the Milky Way. Our nearest stellar neighbor, Proxima Centauri, is a red dwarf. TRAPPIST-1, with its 7 Earth-sized planets packed tightly around a cool dim star, is another, in the hunt for alien life. Many astronomers now think most potentially habitable planets may be found around stars like these. So if we ask, is the universe friendly to life? We are really asking, are red dwarf systems friendly to life? If our own sun had been one, would that make our existence more likely, or almost impossible? On paper, there is a powerful promise. Red dwarfs burn their fuel slowly and can shine for trillions of years. Optimistically speaking, that is an almost unimaginable span of time for biology and even civilizations to rise, fall, and rise again. Compared to the sun's roughly 10 billion year lifetime, a red dwarf feels almost immortal. But while the lifetime is generous, the conditions can be brutal. The Goldilocks zone hugs close to the star, sometimes tens of times closer than Earth's current orbit. Planets there are often tidally locked, with one hemisphere an endless day and the other an eternal night. Many red dwarfs unleash powerful stellar flares that can strip away an atmosphere and bathe the surface in high-energy radiation. So, is a red dwarf sun a cosmic upgrade, or a slow, hostile trap? So, let's begin. In this video, we will rebuild our solar system around a red dwarf, compare it to real neighbors like Proxima Centauri and TRAPPIST-1, and by the end, decide whether we would actually choose to live under a blood-red sky if we had the option. So it's time to find out the truth. Why red dwarfs decide the fate of alien life? If we want to know whether a red dwarf sun is a blessing or a curse, we first have to understand one uncomfortable truth. In the hunt for alien life, our kind of star is the exception, not the rule. Red dwarfs, or M-dwarfs, make up roughly 70% of all stars in the Milky Way. This means that if life is common anywhere in our galaxy, statistically, it probably evolved around a red dwarf, not a sun-like star. Our entire picture of a typical habitable planet might be biased by the one system that is actually weird. It should be noted that even among the closest stars to us, from Proxima Centauri to Barnard's star, red dwarfs dominate the landscape. But while the sun bathes Earth from a comfortable distance of 150 million kilometers, a red dwarf is much dimmer. To receive the same energy, a habitable planet has to move inwards, way inwards. For many M-dwarfs, the Goldilocks zone is 10 to 100 times closer than Earth's orbit, often tucked well inside Mercury's current path. A year might last only a few days. Gravity from the star becomes much stronger, tides stretch the planet, and over time, most of these worlds become tidally locked, showing one face to the star forever. So instead of a world with day and night, you get a planet with a permanent day side and a permanent night side, stitched together by a thin ring of eternal sunset. The atmosphere, if it survives, has to move heat from one hemisphere to the other just to keep the surface from freezing solid or boiling away. And all of this is happening right next to a star that can be either a gentle, long-lived campfire or a violent magnetic beast. Here is the central difficulty. Red dwarfs burn their fuel so slowly that they can shine for trillions of years. Optimistically speaking, that gives life an absurd amount of time to start, adapt, and maybe even outlive the entire visible universe. But many M-dwarfs also unleash powerful flares and high-energy radiation that can erode atmospheres and sterilize the very planets sitting in their habitable zones. Are these stars cosmic cradles of biology or quiet executioners? So, let's begin to stress test our own story. By imagining the sun as a red dwarf, we are taking the conditions that allowed Earth's oceans, climate, and biosphere to emerge, and dropping them into the most common kind of stellar system in the galaxy. If our recipe for an Earth-like world fails there, that has huge implications for how rare we really are. So it's time to find out the truth about our specific what-if. In the next part, we will pin down a concrete Red Dwarf template, compare it to TRAPPIST-1 and Proxima Centauri, and then ask, once we shrink and cool the sun, what happens first, Earth's orbit or Earth itself? Meet the Red Dwarf archetypes, TRAPPIST-1 and Proxima. To anchor this what-if in reality, we need real red dwarfs we can point to. Otherwise, our red dwarf sun is just an abstract idea, drifting in the dark. So, let's begin with the system that has become the icon of small stars and tightly packed worlds, TRAPPIST-1. TRAPPIST-1 is a tiny, ultra-cool red dwarf about 40 light-years away. It has only about 9% of the sun's mass, and is only slightly larger than Jupiter in size, yet it is still far more massive than any planet. This means its light is incredibly faint compared to our sun. To receive enough energy to be even potentially habitable, its planets have to huddle very close in, deep inside what we would think of as Mercury's orbit. And TRAPPIST-1 does not disappoint. It hosts 7 Earth-sized planets, all of them rocky, all of them packed into orbits closer than Mercury is to our star. Some complete a year in just a few days. Several sit in or near the Goldilocks zone, where liquid water could exist. In the hunt for alien life, this system has become a poster child for what a red dwarf planetary family might look like. But while TRAPPIST-1 is small and dim, it is also relatively calm for a red dwarf. It flares, but far less violently than many of its cousins. It should be noted that this quieter behavior may help its planets retain atmospheres, giving TRAPPIST-1 and its siblings at least a fighting chance to be truly habitable. If we imagined our sun as a very low-mass red dwarf, TRAPPIST-1 is one natural template. Now for a pattern interrupt. Let's leave that distant system for a moment and look next door. Our closest stellar neighbor, Proxima Centauri, is also a red dwarf. It is even a little more massive than TRAPPIST-1, yet still far below the sun, and it hosts at least one roughly Earth-mass planet, Proxima b, right in its habitable zone. Sounds perfect, right? A nearby, almost Earth-like planet in the Goldilocks zone of the closest star in the universe to us. So it's time to find out the truth about what that really means. Proxima is violently active. It unleashes powerful stellar flares and intense ultraviolet and X-ray radiation that can strip away a planet's atmosphere over time. Proxima b might be bathed in energy bursts that make stable, surface life extremely difficult. TRAPPIST-1 and Proxima together give us a spectrum of red dwarf behavior, from relatively quiet to aggressively flaring. Optimistically speaking, our hypothetical red dwarf sun could sit somewhere in between, not matching either one exactly. We will use their masses, temperatures, and luminosities as guideposts, then ask if we dial our sun down into that range. Does Earth end up more like a TRAPPIST-1 world, like Proxima b, or as something far stranger altogether, rewriting the sun, shrinking it into a red dwarf? So if we actually dial our sun down into that TRAPPIST-1 and Proxima range, what does our star become? We are not talking about magically cooling the current sun overnight. Instead, we are rewinding the clock and asking a different question. What if, 4 to 6 billion years ago, the star that formed in our place had been a red dwarf from the very beginning? So, let's begin by specifying that star. In this alternate solar system, our sun is not a one-tune copy of TRAPPIST-1, which is only about 9% of the sun's mass. It is more like a modest red dwarf, with roughly 0.2 to 0.3 times the sun's mass. This means the entire system forms around a star only 20 to 30% as massive as the one we know, with a radius shrunk to roughly 1/3. It should be noted that such a star would not shine white-yellow. Its surface would sit closer to 3000 to 3500 Kelvin, glowing a deep orangered ember in the sky. But while the color shift is dramatic, the real shock is how dim this star becomes. A 0.2 to 0.3 solar mass red dwarf would radiate only about 1 to 2% of the sun's current luminosity. In the hunt for alien life, that kind of energy budget is everything. This means the classic Goldilocks zone, the region where liquid water can persist on a planet's surface, collapses inward. Instead of stretching from roughly Venus to just beyond Earth's orbit, it tightens to a tiny ring, perhaps 5 to 10 times closer to the star. Earth's familiar 1AU orbit would be frozen, far outside any habitable band. So it's time to find out the truth about what this really buys us. By shrinking the star's mass and light output, we also weaken its gravitational grip. Planetary orbits can move inward and still remain stable. In fact, for a world to receive Earth-like energy from this red dwarf, it would need to orbit in just a few percent of our current Earth-Sun distance on a year that might last only a handful of Earth days. That is exactly the regime we see in compact systems like TRAPPIST-1. This is where our red dwarf sun becomes a powerful verdict tool. We can now systematically slide each planet inward, matching it to the new Goldilocks zone and asking what happens to its orbit, its atmosphere, and its climate. Does an Earth-like world end up pleasantly warmed by a long-lived, gentle heater with trillions of years for life to evolve? Or does it become tidally locked, one side scorched under constant starlight, the other frozen in eternal night, its atmosphere stripped by flares? Optimistically speaking, this configuration could be either paradise or disaster. In the next section, we will take Earth first, move it into that tight red dwarf orbit, and see which future our planet actually gets. Two futures: cozy hearth or cosmic death lamp. So, which future are we really talking about for a red dwarf sun, a cozy hearth, or a cosmic death lamp? In the hunt for alien life, red dwarfs sit right at the center of this question because they force us to choose between time and tenderness. On one side, the hearth scenario is incredibly tempting. A red dwarf burns its fuel slowly, glowing dimly but steadily for up to trillions of years. This means its Goldilocks zone, although close in, can stay stable far longer than our sun's roughly 10 billion year main sequence lifetime. If Earth had always orbited such a star, life would not just have had a few billion years to experiment. It could, in principle, have hundreds or thousands of times more cosmic time to adapt, diversify, and maybe even survive long after brighter stars have faded. Imagine a universe in the far future where almost every sun-like star is gone. The only lights left are these tiny red embers, each with a tight ring of planets pressed close for warmth. In that picture, a red dwarf sun looks like a shelter, a long-term refuge where an Earth-like planet can orbit safely, while the rest of the cosmos slowly goes dark. But while the timescale is generous, the environment may not be. On the other side of the coin, the same configuration can turn our gentle hearth into a death lamp. Because the habitable zone is so close, any planet that wants to stay warm has to huddle right up against the star. That puts it directly in the line of fire of frequent high-energy flares, intense stellar winds, and ultraviolet radiation. It should be noted that many red dwarfs are far more magnetically active than our sun, especially when they are young. Over hundreds of millions of years, that repeated blasting could strip away an atmosphere, boil off oceans, and leave a bare rock. And even if the atmosphere survives, the orbit itself comes with a cost. Tidal forces will almost certainly lock a habitable planet so that one hemisphere faces the star forever, while the other never sees daylight. One side bakes under constant red glare, the other freezes in permanent night. Between them, a narrow twilight band might remain truly habitable if winds and oceans can move heat around. So it's time to find out the truth. Is that narrow strip a reasonable home for life, or a desperate compromise? So the core question becomes sharper. If Earth had to orbit a red dwarf to stay warm, is that fundamentally a better deal for life than the bright but brief stability of our current sun, or is it a poison chalice wrapped in the promise of trillions of years? Optimistically speaking, the answer is not obvious. As we walk planet by planet through a red dwarf version of the solar system, we will see some worlds become surprisingly more promising, while others are instantly doomed by the new architecture. And here is the twist. Before we can judge Earth's fate, we need to redraw the entire layout. Because the first casualty of a red dwarf sun might not be Earth at all, but a very different kind of planet we currently take for granted. Your guide through the red dwarf solar system, and here is the twist. Before we can judge Earth's fate, we need to redraw the entire layout. Because to navigate a red dwarf version of the solar system, we need a guide. And this is, where we take the wild what-ifs of the universe and run them through real physics. In the hunt for alien life, it should be noted that speculation is easy. The hard part is treating each scenario like a controlled experiment, with rules we do not allow ourselves to break. So, let's begin by setting those rules. First, we will define what kind of red dwarf our sun becomes, its mass, its temperature, its dim, red glow compared to today's bright yellow-white star. This means working out how its luminosity drops, how its Goldilocks zone collapses inward, and how close a planet now has to orbit just to receive Earth-like energy. Then, we will rebuild the solar system from the inside out. We will ask, if Mercury, Venus, Earth, Mars, and the outer worlds were somehow transported into this new compact red dwarf system, where would they land? Who ends up in the new habitable zone? And who is exiled into deep freeze or locked into permanent fire? Pattern, interrupt. When we say habitable zone, it sounds comforting, almost Earth-like, but around a red dwarf, that zone can be 10 to 100 times closer to the star. Planets there are likely tidally locked, with one side in endless day and the other in eternal night. So it's time to find out the truth. Does being in the right orbit still mean anything when half your surface never sees a sunrise? We will move world by world. Mercury, stripped of its role as the innermost planet, might suddenly find itself much farther out, a frozen relic instead of a scorched rock. Venus, with its runaway greenhouse atmosphere, will test whether any world with that kind of climate can survive closer to a flare-happy red dwarf. Earth will be our main experiment. We will track its new orbit, its new spectrum of light, and ask whether oceans, weather, and life can adapt. Mars will show us what happens at the cold edge of this compressed system, while the gas giants and icy moons reveal whether distant reservoirs of water and organics become more or less promising. Optimistically speaking, some of these outer regions might even move closer to the action. The high-level goal is simple to state and hard to answer. If an advanced civilization could choose its star, should it pick a short-lived sun like ours, or roll the dice on a red dwarf that burns for trillions of years? As we go, start keeping score in your head. Which star would you choose, right now? Hold that thought, because by the end, after we have watched a red dwarf sun reshape every orbit and every atmosphere, we will come back to that decision. Red Dwarfs 101, Rules of a Smaller, Redder Universe. So, let's begin by laying down the basic rules of a red dwarf universe, because if we shrink the sun, we have to play by those rules whether we like them or not. Red dwarfs are the lightweights of the stellar world. They range from about 8% of the sun's mass up to roughly 60%. This means far less gravity squeezing their cores, lower pressures, and cooler nuclear fusion. Instead of the sun's surface temperature of nearly 5800 Kelvin, a typical red dwarf glows at only about 2500 to 4000 Kelvin. It would look dimmer, redder, and more ember-like than the bright white-yellow disk we know. But while the drop in temperature is important, the real shock is luminosity. Because of the steep mass-luminosity relationship, a red dwarf can shine with only a few percent or even a few thousandths of the sun's light. This means a planet like Earth, left at 1 astronomical unit, would freeze into a deep space snowball. To get Earth-like warmth, the Goldilocks zone has to collapse inward. How far inward? In the hunt for alien life around these small stars, we find that the habitable zone can be 10 to 100 times closer than Earth's current orbit. A world might circle at just a few million kilometers, completing a year in days instead of 365. TRAPPIST-1's planets, for example, all fit well inside Mercury's orbit, and some whip around their star in less than 2 Earth weeks. This is the kind of compact system our own planets would need to imitate. It should be noted that this extreme closeness comes with a price. Strong tidal forces tend to slow a planet's rotation until one side permanently faces the star. Tidal locking turns day and night into fixed hemispheres, a scorching day side and a frozen night side, unless the atmosphere and oceans can move heat around efficiently. On top of that, many red dwarfs are magnetically restless, unleashing frequent flares and high-energy radiation. These can strip atmospheres, erode ozone layers, and bathe any surface life in ultraviolet and X-rays. Optimistically speaking, the one big advantage red dwarfs offer is time. They burn hydrogen so slowly that their main sequence lifetimes stretch into the hundreds of billions, even trillions, of years. Our sun's comfortable phase lasts around 10 billion years. A red dwarf can outlive it by a factor of 100 or more. So it's time to find out the truth. Are these long-lived stars gentle cradles for life, or slow-motion hazards? Because when we turn the sun into a red dwarf, all of this becomes personal. The habitable zone moves inward, Earth's orbit must shrink, years shorten, and tidal locking and flares stop being abstract problems and start rewriting our climate. In the next section, we will ask the uncomfortable question, where would Earth have to move? And what would that new orbit actually feel like? Designing our red dwarf sun, specs and personality. So if we are going to move Earth, we first need to know, what exactly are we moving it around? We cannot just say a red dwarf and leave it vague. In the hunt for alien life, details matter, and our alternate sun needs a clear identity. So, let's begin by choosing its basic specs. We will dial the sun down to about a quarter of its current mass, roughly 0.25 solar masses. This means its gravity is weaker, its core pressure is lower, and it shines far less brightly. The radius shrinks to about 30–35% of today's sun, and the luminosity drops to around 1–2%. The surface temperature falls to roughly 3300 Kelvin, turning our familiar yellow-white star into a cool, deep red dwarf. How does that compare to real red dwarfs we know? TRAPPIST-1 is even more extreme, only about 9% of the Sun's mass, smaller than Jupiter in size, and less luminous than our redesigned star by an order of magnitude. Proxima Centauri, on the other hand, is closer in mass to our choice, but still slightly lighter and cooler. So our red dwarf sun sits between these examples, a mid-range M-dwarf, not ultra-cool and tiny like TRAPPIST-1, not as quiet as the calmest dwarfs, but not the most violent either. But while its light is gentle, its magnetic personality is not. It should be noted that red dwarfs of this mass often have powerful magnetic fields, especially when young. These fields twist and snap, launching frequent flares and coronal mass ejections. Intense ultraviolet and X-ray bursts can slam into any nearby planet, heating and stripping the upper atmosphere. This means that, early on, our Earth-like world would be sitting under a space weather siren, not a peaceful sky. Compared with TRAPPIST-1, which JDOS suggests is surprisingly calm for such a small star, our red dwarf sun is moderately active. Compared with Proxima, famous for violent megaflares, it might actually be a little better behaved. Optimistically speaking, that places it in a middle category, dangerous, but not automatically a death sentence for atmospheres. Now for the new Goldilocks zone. To receive the same energy Earth gets today, a planet would need to orbit much closer in, roughly 0.1 to 0.2 astronomical units. That pulls the habitable region well inside Mercury's current orbit. Orbital periods shrink dramatically. Instead of 365 days, a year might last only a few weeks to 2 months. Seasons, if any, would race by. So it's time to find out the truth. Could Earth survive in that tight embrace? Would it tidally lock, lose its atmosphere, or adapt? In the next section, we will move our planet inward and discover what a year under a red dwarf sun would actually feel like. Rebuilding the solar system around a red ember. So, if a red dwarf sun pulls Earth inward, what happens to everything else? We cannot just move one planet, the entire solar system has to be rebuilt from scratch. When a small cool star forms, it does not get the same cosmic budget our real sun enjoyed. A red dwarf like this hypothetical mini-sun would have a lighter, more compact protoplanetary disk. This means there is less raw material spread out over space, and gravity keeps what is there huddled closer to the star. It should be noted that, in such a system, giant planets like Jupiter and Saturn are far less likely to form, while rocky worlds crowd the inner regions. So, let's begin with the new map. Because the star is so dim, the Goldilocks zone collapses inward. Instead of sitting around 1 astronomical unit, where Earth currently orbits, the habitable region might lie near 0.1 AU, or even closer, roughly where Mercury is now. At that distance, a planet would receive a similar energy budget to modern Earth, just in a redder, softer spectrum. Meanwhile, Earth's old orbit at 1 AU is no longer mild and blue. It is pushed far beyond the new snowline, into a realm where water, carbon dioxide, and even many gases freeze out. Our familiar position becomes a deep freeze desert. Orbital rhythms change just as dramatically. A planet parked in this inner Goldilocks zone at about 0.1 AU would not take 365 days to complete a year. Instead, it might whip around the star in only 20 to 30 days. Seasons, tides, the length of a year for any life that might arise there, everything is compressed. But while the inner system speeds up, Mars-like distances crawl. A world placed out near where Mars orbits today would take several years to complete a single circuit, drifting through bitter cold around a faint red point in the sky. Here's the pattern interrupt. Picture our entire solar system squeezed inside Mercury's current orbit that is closer to the architecture we expect. In the hunt for alien life, we have already seen something similar. The TRAPPIST-1 system packs 7 Earth-like planets into a space smaller than Mercury's path, all locked in tight orbital resonances. Optimistically speaking, our alternate red dwarf solar system might look like a scaled-down, less crowded cousin of TRAPPIST-1, with a handful of rocky planets marching in close formation. So it's time to find out the truth about our own worlds in this miniature system. When we drop Mercury, Venus, Earth, and Mars into these new orbits, some will land squarely in the habitable zone. But does that automatically make them habitable, with stable atmospheres and friendly climates, or does the red dwarf turn them into airless, scorched, or frozen husks? In the next section, we will test each familiar planet one by one. Earth's new address, from blue marble to tidal prison. So, if some of our familiar worlds now sit in this compressed Goldilocks zone around a red dwarf sun, what about the one that matters most to us? In the hunt for alien life, we usually look outward, but here, we're turning the telescope back on Earth itself. Could an Earth-like planet in that tight, dimly lit orbit really stay blue, with oceans, clouds, and a breathable atmosphere? Or, under a red dwarf star, does habitable zone quietly translate to tidal prison, a place that looks safe on paper but is locked, scorched, and frozen all at once? To match the warmth we receive today, Earth would have to move dramatically inward. Instead of circling at 1 astronomical unit, it would orbit at roughly 0.1 to 0.15 AU, 10 times closer to the star. This means the sun would loom several times larger in the sky, burning dull red instead of white-yellow, and our year would shrink to perhaps 20 to 40 days. Seasons would be less about tilt and more about how the star's activity changes over just a few orbits. But while the incoming energy might be similar on average, the tides would be completely transformed. At that distance, the gravitational pull from the star would flex our planet far more strongly, raising larger tides not only in the oceans but in Earth's crust itself. Over time, those relentless tugs act like a cosmic brake, draining rotational energy and reshaping the very rhythm of day and night. It should be noted that this is exactly what we see in many compact red dwarf systems. Close-in planets tend to become tidally locked. One hemisphere ends up permanently facing the star, locked in endless day, while the far side is plunged into eternal night. Instead of a spinning globe with sunrise and sunset, you get a world with a fixed day side, a fixed night side, and a narrow twilight ring between them. So it's time to find out the truth. On such a tidally locked Earth, could complex life really thrive? Would the day side bake into a desert furnace, with oceans boiled away into thick clouds, or stripped by flares? Would the night side collapse into a frozen wasteland, where the atmosphere itself snows out onto the ground? And is the thin Terminator zone, that permanent copper-red sunset band, the only potentially habitable strip left, whipped by colossal winds trying to move heat from day to night? Optimistically speaking, some climate models suggest that, with a dense enough atmosphere and oceans, heat could be redistributed, softening those extremes. But other simulations, and real data from systems like TRAPPIST-1, hint that atmospheres may be fragile under a red dwarf's radiation. So before we decide Earth's fate in this scenario, we need one more piece of the puzzle. How do Mercury, Venus, and Mars behave when we drop them into these new orbits? Do they point to survival, or to a pattern of worlds stripped bare? The answer to that will tell us whether our blue marble could adapt, or whether the red dwarf turns the inner solar system into a warning. A universe of guesses, limits of our red dwarf crystal ball, so how sure can we really be about any of this? If we cannot actually swap out our sun for a red dwarf and hit record on the solar system, how much of this is science and how much is educated guesswork? It should be noted that what we are doing here is a thought experiment built on layers of models. We take the real physics of orbits, tides, and radiation. We plug in what we know about red dwarfs from systems like TRAPPIST-1 and Proxima Centauri. Then we let computer climate models loose on an Earth-like planet in this new Goldilocks zone. This means every result depends on assumptions we feed in. In the hunt for alien life, red dwarfs are tempting because they are everywhere, but while they are common, they are also tricky. For TRAPPIST-1, Joblist has already surprised us by showing that some inner planets are almost airless, where we expected thick atmospheres. If the real planets can mislead us, how much more cautious should we be about a purely hypothetical red dwarf sun? Our knowledge of red dwarf habitability is evolving almost month by month. New telescopes are still measuring how often these stars flare, how powerful those flares are, and how far their high-energy radiation reaches. At the same time, 3D climate simulations are testing whether an atmosphere on a tidally locked world can move heat from the day side to the night side fast enough to stay habitable. So, let's begin with some humility. The story is not finished. When we talk about Earth tidally locking, losing its atmosphere, or freezing into a day-side, night-side world under a red dwarf, we are leaning on the best models available today. But those models come with wide error bars. Some show thick atmospheres surviving for billions of years. Others predict that repeated flares strip them away. Which one is right? At this point, scientists genuinely disagree. Optimistically speaking, red dwarfs might offer stable light for trillions of years, giving life enormous time to adapt. Pessimistically, their magnetic tempers might sterilize many worlds before biology gets a foothold. So it's time to find out the truth? Not yet. Right now, we are mapping out possibilities, not delivering a final verdict on whether red dwarfs are net good or bad for life. Still, this does not mean our scenario is meaningless. Some broad trends are very robust. Dimmer stars force their habitable zones inward. Closer orbits strengthen tides and make tidal locking likely. Long lifetimes extend the window for evolution. Higher flare rates raise the risk to any atmosphere. Even as the details shift with new data, these patterns hold. So as we drop Mercury, Venus, and Mars into their new orbits, keep that in mind. We are not predicting the exact weather on any one world. We are testing which way the balance tilts. In this red dwarf solar system, do the inner planets cluster toward survival or toward silence? Our next step is to watch how each one responds. Winners and losers. Who enters the new habitable zone? So in this reshaped solar system, who actually wins? Who ends up in the new Goldilocks zone? And who is pushed out into permanent darkness or relentless heat? To answer that, we first need to sketch where a red dwarf sun would keep water liquid. Our original sun pours out a lot of energy. A typical red dwarf of similar mass would be far dimmer, so the habitable zone collapses inward. Depending on the exact luminosity we choose, the sweet spot now sits somewhere around 0.05 to 0.2 astronomical units. This means the entire region that used to span Mercury through Mars is compressed into a tight furnicillate band. It should be noted that 0.05 AU is only about 1/10 of Mercury's current distance, while 0.2 AU is still well inside Venus's present orbit. So, let's begin by simply sliding our familiar planets into this new framework. Mercury's original path at about 0.39 AU is now far outside the red dwarf's main heat lamp. If we keep the same orbital distance, it freezes. But if the whole system migrates inward so that Earth ends up near the middle of the new zone, Mercury's relative position would place it close to the inner edge, flirting with runaway heating and intense stellar radiation. Venus and Earth analogs in that scaled-down layout would straddle the middle of the band, where starlight is neither overwhelmingly strong nor desperately weak. Here, surface conditions are set by atmosphere and rotation, rather than just raw flux. Mars, pushed outward in this compact system, might find itself near or beyond the cold outer edge, where even a thick greenhouse atmosphere struggles to keep oceans from locking under ice. In the hunt for alien life, this is the gray territory of marginal habitability. If that pattern sounds familiar, it should. TRAPPIST-1 compresses 7 Earth-sized planets into a span smaller than Mercury's orbit. Our hypothetical red dwarf sun would do something similar on a slightly larger scale. Multiple roughly Earth-like worlds could share this narrow ring, each tidally stressed, each showing the same star-facing hemisphere forever. Instead of one comfortable Earth, we get a chain of near misses, some too hot, some too cold, a few hovering in between. Optimistically speaking, that is not all bad news. Pack several rocky planets into a close habitable zone, and you actually increase the amount of potentially habitable real estate inside a smaller volume of space. Worlds can trade material, swap comets, and maybe even exchange life, if it ever arises. So it's time to find out the truth. Which of our inner planets could actually take advantage of this opportunity? In the next segments, we will walk Mercury, Venus, Earth, and Mars through this red dwarf spotlight, one by one. Who becomes a permanent hell world, who freezes solid, and who might quietly transform into a refuge against all expectations. Inner worlds remixed, Mercury, Venus, Earth, and Mars under red light. So, let's begin with the inner worlds themselves. If our sun had always been a red dwarf, the entire Goldilocks zone would shrink inward until it practically brushed the star's surface. Every familiar orbit would be remixed. Mercury, Venus, Earth, and Mars would all need new seats in this compact, high-stakes system. Our Mercury analog would live dangerously close in. Picture a small rocky planet hugging the red dwarf at a distance similar to TRAPPIST-1b or 1c. A year might last just a day or two. Tidal forces would almost certainly lock one face toward the star, freezing the rotation. The day side becomes a permanent furnace, the night side, an airless deep freeze. Under constant flares and high-energy radiation, any early atmosphere is stripped away. It should be noted that DRESS data for TRAPPIST-1b and 1c already show worlds like this, effectively airless, hotter than Mercury and sunlight, yet still cooler than expected, because bare rock radiates heat straight into space. Our Mercury, in the hunt for alien life, is simply a dead, irradiated stone. Move one step out and the Venus analog enters the frame. Here we have a slightly larger rocky planet near the inner edge, or perhaps the middle, of the habitable zone. Gravity is strong enough to hold a dense atmosphere, but does that help or hurt? A thick CO envelope could buffer the surface from brutal flares and smooth out the temperature difference between day and night on this tidally locked world. This means clouds and winds might circulate heat efficiently, keeping a broad band of the surface above freezing. Or the same blanket could run away into a super greenhouse, like an even more extreme Venus, with surface temperatures of hundreds of degrees. TRAPPIST-1d sits in a similar regime, and JUST has not yet found clear signs of water or CO, leaving its true nature mysterious. Our red dwarf Venus could be a shielded oasis, or a permanent pressure cooker. Now we arrive at the Earth analog, the main prize. Same mass, similar gravity, but in a dramatically tighter orbit, perhaps like TRAPPIST-1e or Proxima b. A year might last just a few days, almost certainly tidally locked again, with one hemisphere locked into endless red daylight and the other in eternal night. Yet this is where things become truly interesting for life. If the planet keeps a substantial atmosphere, winds and jet streams can transport heat from the dayside into the darkness, creating a temperate terminator ring where ice, liquid water, and clouds coexist. JUST has already ruled out some extreme atmospheres for TRAPPIST-1, suggesting a more Earth-like balance is still possible. Optimistically speaking, our red dwarf Earth could host oceans under a crimson sky, with civilizations living in a perpetual twilight band. Finally, the Mars analog drifts near or beyond the outer edge of the habitable zone. Smaller, with weaker gravity, it struggles to hang on to its air, while flares constantly erode the upper atmosphere. It ends up more like TRAPPIST-1, cold, low pressure, likely icy. Perhaps thick greenhouse gases or subsurface aquifers could keep pockets of water liquid, but long-term surface habitability is unlikely. So if this is the new inner solar system, what happens to everything beyond Mars when the sun is a red dwarf, and could the real surprises be hiding there instead? Would we choose the red dwarf? Verdict on life and civilization. So if the outer solar system shifts inward, and the inner worlds freeze or fry in strange new ways, what kind of long-term home does a red dwarf really offer us? Because in the hunt for alien life, we are not just asking where microbes might cling on, we are asking where civilizations like ours could actually thrive. On our transformed Earth, the verdict is harsh. We end up as a tidally locked planet, one face staring at a blood-red sun, the other an eternal night. Habitability collapses into a narrow twilight band, where retreats to subsurface oceans insulated by ice and rock. It should be noted that this strip could remain stable for trillions of years, far longer than our current sun's main sequence life, but it would exist under constant environmental stress, flares, radiation storms, and slow atmospheric loss, reshaping the climate again and again. This leads to a strange contrast. A red dwarf star offers an almost unimaginable timeline. While our sun gives us roughly 10 billion years, many red dwarfs sip their fuel so slowly they can shine for thousands of billions of years. Optimistically speaking, that is a vast canvas for life to arise, evolve, and adapt. This means that, on paper, most of the habitable real estate in the universe might orbit these dim, red stars. But while the long timeline is inviting, the early years are brutal. Young red dwarfs can flare violently, bathing any close planet in X-rays and charged particles. Many worlds may lose their atmospheres before life has a chance to build complex ecosystems. TRAPPIST-1, relatively quiet for a red dwarf, still challenges its planet's atmospheres. Around a more typical star, how many Earth-like worlds are stripped bare before they ever enter a calm, habitable phase? Now imagine a civilization trying to rise in that environment. Frequent flares would threaten power grids, satellites, and any unshielded surface technology. Space travel would mean threading through radiation storms. But there is a twist. Those same hazards might push intelligent species to master shielding early, build underground or underwater habitats, and develop planetary-scale engineering just to survive. Would that slow them down, or force them to become more resilient more quickly? So it's time to find out the truth about our own preference. For complex, surface-dwelling life that relies on stable climates and gentle seasons, a sun-like star may be a sweeter spot, shorter-lived, but calmer and more forgiving. Red dwarfs might favor hardy biospheres that evolve slowly in protected niches, or civilizations that live mostly beneath rock, ice, and engineered domes. If humanity could choose its star, would we really trade our relatively calm yellow sun for a temperamental red dwarf with a trillion-year future? Knowing what we now know about flares, tidal locking, and Resorthan Goldilocks zones, the answer is not obvious, and it raises one last question. If we stay with the star we have, can we learn to reach those distant red systems instead? Your turn. Pick our star and rewrite the future. If we stay with the star we have, what does that really mean for our future? Because in this journey, we have already lived through another version of the story. We began by waking up under a blood-red sky, asking what would happen if our familiar yellow sun were replaced by a small, cool red dwarf. Step by step, we rebuilt the entire solar system. We dragged Earth inward into a new tight orbit, compressed the Goldilocks zone until it hugged the star, and watched Mercury, Venus, and Mars either fry, freeze, or cling to narrow strips of habitability. Then we stress tested it all under real red dwarf behavior, violent flares, brutal radiation, and the strange physics of tidal locking that could leave one side of a planet an eternal day while the other never sees the star at all. In the hunt for alien life, this is not just a dramatic thought experiment about us. This means we are rehearsing what most potentially habitable worlds in the universe actually face. It should be noted that red dwarfs are the dominant stars in our galaxy, and their planets, packed close in, are the places our telescopes keep finding Earth-like sizes and promising orbits. When we imagine atmospheres being stripped, night-side ice oceans, or narrow twilight bands where liquid water might survive, we are really asking what life is up against almost everywhere. So, let's begin to weigh the trade. On one side, a star like our Sun, brighter, more stable, with a Goldilocks zone comfortably far out, and a few billion years of relatively calm conditions for complex life to arise. On the other, a red dwarf, faint and temperamental, but capable of burning steadily for trillions of years, outliving our Sun many hundreds of times over. But while the red dwarf offers immense time, it demands resilience against flares, tidal locking, and resource habitable regions. Which environment gives civilizations a better chance, not just to appear, but to endure? So it's time to find out the truth about our preferences. If humanity could choose its star, which would you pick? Would you stay with a short-lived but gentle yellow sun, or gamble on a long-lived red dwarf system, accepting harsher early conditions in exchange for almost endless time? Tell us in the comments which star you would choose for humanity and why. And while you are there, suggest other wild but physics-grounded what-ifs you want us to explore next. Different stars, different orbits, or entirely new planetary systems. Optimistically speaking, every clear night is a chance to test this for yourself. Step outside, look toward the fading glow of our ordinary sun, and then up at the faint red dots that are distant dwarfs. Somewhere out there, under dim red light, another world's story is unfolding. In another universe, that could have been Earth's story too.